Thanks. Hi, everybody. As already introduced, I'm Konstantin. This is my insanely long Twitter handle. If you feel like following me on Twitter, now might be the time, so you pay attention later. In case you don't know me, I'm rather active in open source. I'm the maintainer of Sinatra. I'm on the rec, the tilt team, etc. Done some work on Rubinius and a lot of other projects. And last year, together with Alan Harris, I also wrote a book about Sinatra, which you can buy from O'Reilly. And if you use that coupon code there, it will give you a 50% discount, which makes it like six US 50. That is what, €3 or something? And I currently work at a company called Travis CI. Who in here has not heard of Travis? Okay, 1 or 2, 3. I think that one was fake. It's fully open source. We do continuous integration as a service. And we currently live off donations. And those company logos there are our main donors like Cloud Control, Ruga, Bandyworks, Sing, etc., etc. Special thanks to donors that are here, like Heroku, Dana Simple, Engine Yard. They have all given us money just to make sure that we can work full-time on this. And I have the pleasure of working with that guy. And this guy. Well, actually, if you could do me or us a favor, this is Josh. And today is his 30th birthday. So take out your computer and send him a happy birthday tweet. Here is a template you may use if you feel like it. And while you're at it, if you feel really generous, our crowdfunding campaign is also still running. And it has been successful, really successful already, but we're currently 4 full-time developers, so money doesn't actually last that long. We would really appreciate it. Depending on the amount you would give us, you get pair programming with $10 or just some cool stickers. You get into our private build, beta, anything, and we would really appreciate it. But now to my talk. So Ruby 1.8 is slow because it's interpreted. We all know that. Ruby 1.9 has a VM, that's why it's fast. But surprise, surprise, Ruby 1.9 is interpreted too. Thanks. Okay, so let's talk more about Ruby. Oh yeah, talk isn't over yet. Let's talk more about Ruby. To be exact, let's talk about the internals and how those internals try to achieve performance. But be warned, this talk is extremely technical, and just try to bear with me, even if you should see some C code, for instance, which it is not necessarily to understand everything that's going on there. It's just I want to give you an idea of what Ruby looks like under the hood. Well, and actually, what is Ruby? Well, Ruby is obviously the language, and Ruby is also the implementation. Well, to be honest, there is a ton of Ruby implementations out there. And we just heard about one of the implementations. I'm going to focus on the large 3 ones, which are those most compatible to each other. Ruby 1.9, JRuby, and Rubinius. And we want to look into how they perform, how they try to achieve performance. To be more exact, we want to look at the method dispatch and method execution, how that is implemented in the Ruby 1.9 VM. Then we're going to look into some optimizations, mainly inline caches and jitting on Rubinius and invokedynamic on JRuby. It doesn't mean that the other implementations don't do all of that. Like MRI does not do jitting, but both JRuby and Rubinius do that. I can explain it in a bit. It's just that I want to look at those implementations under those aspects. And the code we're looking at is this code. It's basically just a class implementing one method that checks if the value is the ultimate answer. And it accepts both integers and strings or anything that converts to it. And so one thing you have to know about Ruby implementations, they just love bytecode. Take this really, really simple Ruby code. If you compile it and then look at the textual representation of the bytecode instead of just the ones and zeros, because that's pretty hard to grasp, it looks like this on MRI. Okay, there are values in there, 2 S's in there, fair enough. I even prefer the one from Rubinius because it looks like this. Well, we push the first local because we only have one local, so we push the first local on the stack and then send 2S to it with no arguments. And if you do the same thing for JRuby, say on the Jvm 1.6, it looks somewhat like this. I removed some stuff everywhere, but that is mainly due to the JVM bytecode not being made exactly for Ruby. And if you look at that, you might feel like I have no idea what I'm doing here. Trust me, that's how I felt when I first looked at it. So to get a grasp of what we're talking about basically turning Ruby code into machine instructions. And there are a few paths you can take. Like all implementations start off with you have the source code as a text file or a textual representation. You parse that, and the parser turns it into a parse tree, and then you could have an interpreter running it directly. That is what 1.8 does. Or you could compile it to bytecode, which is basically what I just showed you. Just instead of the command get local, they actually have a byte in there representing that command. And then you can interpret it, which is like the classic VM implementation. It's basically like a big while loop with a case statement in there that in the classic implementation that just looks at the first byte and then depending on that executes something like the byte could mean add 1 + 2 or something. But you could also use a JIT, which takes those bytes and transforms them into machine code, which is extremely similar, except that the part that will run that code is not software, but your processor. And the plan is to find a method and to execute a method. But as I said, we want to do it fast. So how do we speed that up? Well, pretty easy. We have to find a method faster and we have to execute it faster. Simple, isn't it? So for finding it faster, we can use an inline cache. I'm going to explain that. Or we can use a lookup cache, which is what MRI uses. It's basically where do you cache. You can do inlining, which actually eliminates finding the methods you call. And that's like the main things, the main tricks you can pull out of your head. And then you can speed up execution. You can reduce operations. It means have one bytecode that does a lot of things. This is actually the direction MRI is heading in there. They're adding something that's called super opcodes. You can do just-in-time compilation. Well, and speeding up search really helps because most time you spend actually looking for what methods to execute and then jumping to that method. If you get that fast, then you're pretty much... That's the most important thing. Okay, so let's look at MRI. When you look for a method in MRI, because you want to run it, then on C level, you usually would call RB method entry, which gives you, for a certain object and a certain method name, it will give you the method entry that you can then execute. And this uses the lookup cache, so it will, if it doesn't have the method reference in the cache, it will call without cache, and that will call search method, which is the actual internal method for finding that object. And it looks like this. I haven't removed any code. It's really simple like that. If you look at it, it's actually looping through all the classes that are inherited. Here it's asking for the superclass and looks at the method table of those classes. Pretty much what you would expect. What? Class ID. What's ID? ID is just the class name, I think. The representation, the identifier. So it actually does the lookup on the class with the... Yeah, it's a selector for the method. Yeah, so basically the method name. And you want to make that run fast. So it then, when you found the method, you hand it to VM call, which has this nice construct of a label in front of a switch, and then in there it says go to again. Everything doesn't matter, it's just a really large bunch of C code. And in here it does VM exec, which actually runs a bytecode. And it looks up what to do about a bytecode in the instruction manual. It's an instruction file which basically lists all the bytecode and what to do about it. And the bytecode for calling another method actually looks like this, the instruction definition for it, and you see down here it actually searches for the method and then calls that method. And that's basically the cycle of life in a Ruby program. And besides the lookup cache, there's not much optimizations in MRI for this right now. But Rubinius and JRuby are really big into optimizing those things. So if we look at Rubinius, the nice thing is that large parts are actually implemented in Ruby. It has a C++ VM, but nearly everything else, including the bytecode compiler, is written in Ruby. And you have a lot of introspection of the objects. So if you have a module, which in this case a class, a module, or an include module, which is when you include a module, all reference to a method table, which is what Rubinius calls a lookup table. So it's a simplified version of a hash. It can only have symbols as keys, etc., etc. In there we have the values, or what Rubinius calls buckets, that keep a reference to compiled method, which is a Ruby object, which is really cool because it means you can play with it. Like if you want to do the method lookup yourself, you would do it like this. You just get the singleton class of an object, because it could have a singleton method just defined on that object. And then you go through all the ancestors. You have to go through the direct superclasses, so you don't miss if there has been a module included that defined the method. And you just look up the method. And then you have the compiled method object. You can get it like up here is just saying method, then this is a compiled method object, and you can inspect it in Ruby. I'll explain that on the next slide. It's just to show you you can do all that in IRB, you can play with it, you can even modify it, which is pretty cool. You could now replace 42 in there with some Ruby code at runtime. You can look at the instructions like this with a decode command, which is super helpful. There's even a command line switch on Rubinius where you can do that, and you can, well, inspect the bytes actually. So let's look at what's going on here. So if you, down here are the literals, 2s, 42, and equals, and those are the byte instructions. And that's all what Rubinius needs to execute or compile it to machine code. I listed this in this view. Up here, again, the value is 42 in our example, and those are the bytes. Now, if you go through the bytes, then the VM will read 20 and knows that for the instruction 20, which is push local, there's one argument. So it's going to read the next argument. It's going to read 20 and 0. It says push local with index 0 onto the stack. Local with index 0 is value, which in that case is 42. So 42 will end up on the stack in memory. The next instruction is send stack, which sends the literal to S, the first literal, with 0, and 0 arguments as a method to whatever is on top of the stack, and puts that instead on top of the stack. So it pops it off and pushes the result on. So 42 as string will be on there. After that, it pushes literal 1, which is 42, onto the stack. So we have 42 on there 2 times. And it duplicates that. That's really important because it's a literal in the code. Otherwise, if you modify it, you will modify it for all subsequent calls to the method. And then there's an optimization for equals equals. It doesn't do a method send unless you override the method. This is speed optimization. And, well, pops off those 2 from the stack, pushes true on there, and then returns whatever is on top of the stack. This is basically how a stack machine works. And for optimizations, Rubinius is now inserting the inline cache at this point of the bytecode. So the first time we get here, this will actually be resolved. It will look for that method, and then for any subsequent calls, it will no longer look for it because it's replaced in there. And if you look at the instruction sequence, then you really see, since all of those instructions are actually Ruby objects, there will be a symbol in there, and that symbol will be replaced by real instance of inline cache. And that inline cache can do more than just caching where the call goes. And of course, if you define more, it has one check. Did the class change? Did the object change? And so if you define a new method, if you override it, then we'll do the full lookup again. And this inline cache then keeps a reference to the VM method, which is the low-level instruction set that is already compiled. And you can specialize those methods. You can change the reference it's pointing at. It might not seem obvious why you would do that. Right now there are the bytecodes in there that the VM can execute directly, but there are a few reasons why you want to change that. And what's important is it can keep a reference to the original version and to the specialized version of a method. And well, the specialized version can have inline caches in there, so you can have different paths with inline caches. It can have breakpoints. This is actually really cool. You can have breakpoints, and then it will only use the breakpoint version if you're debugging through it, which is why Rubinius can have a debugger running on a process without slowing down execution. This is something MRI cannot do. They have to be in debug mode, and then everything is slow. And Rubinius, you can just attach the debugger at any time, and everything else will run at full speed, even be compiled to machine code. Can have special instruction sets just for special arguments you pass in just to make it faster, swap around how an if switch works, etc., etc. And it can refer directly, instead of referring to the compiled method with the bytecode in there, it can refer to a C method, which means that if the object didn't change, all you need is one long jump instruction on the CPU, and then you will be right in machine code, which can be as fast as compiled C code, in some examples even faster. And yeah, that is how Rubinius does that under the hood. And for compiling to machine code, it's using LLVM. I just added that slide to also have the dragon logo in there. So it's turning the Rubinius bytecode into LLVM immediate representation, is what it's called. And then LLVM knows how to optimize that and compile that for different CPUs, so it can run anywhere. Whew. Still following? Okay. Let's talk about JRuby. There's this thing called invokedynamic everyone's buzzing about. What do I need that for? I mean, isn't a JVM awesome? Why do I need a new instruction? Okay, let's once more look at that insanely large bytecode, but this time I removed even more, so just to show you something. If you compile Ruby code on JRuby on the Jvm 1.6, which does not support invokedynamic, it gets compiled to something like this. Invoke virtual get call side, and then and then later it will do an invoke virtual with call side call. Invoke virtual is the bytecode for calling methods. While calling virtual methods, there's also invoke static. So it will actually, on this example object that basically is the execution context, it will say, get the first call side. And this is a Java object. And that Java object knows how to run or how to go to JRuby code, to Ruby code. And on that call side, it will call a call. So no Ruby method is actually invoked here. And the reason why that is that the Ruby dispatch, how methods are looked up, is quite different from the Java dispatch. Otherwise, you could just generate real Java methods there that you call. And the fun thing is that now invokedynamic actually allows you to call methods with a different dispatch logic. So if you would compile the same example, which is just value to s, on the Jvm 1.7, then the bytecode would look like this. You don't have to get the call side anymore, because you don't have to implement the custom dispatch on that level. And it has the 2s already in there. Just says invokedynamic, and I'm going to tell you how to dispatch that. And telling the JVM how to dispatch that looks like this. I'm sorry for... So what you see is it will call that method to s. That method on Java level actually takes 2 arguments, the file it was called in and the line it was called on. That's used for backtraces, etc. There would be more arguments if it would also take arguments in Rubyland. And so you see that actually in here it's passing the thread context and 2 Ruby objects, which are those down here. And then the method will also return a Ruby object. And for dispatch, it's using the JRuby runtime invokedynamic invocation linker. And this linker has, as you can see, a bootstrap method. This linker has more. This linker has a bootstrap, a guard, and a fallback. That is whatever you use for invokedynamic, like all the time. Now, the first time the JVM executes that code, the invokedynamic call side will not be set up yet. So what it does is it calls the bootstrap method. The bootstrap method says, okay, please, so what the JVM is saying is, please look up that, set everything up you need to do, I want to call that method. And then it goes there, fetches the JVM method, and keeps a reference to it. That's what it would do in the normal implementation. JRuby doesn't fetch the method in the bootstrap. And for any subsequent call, JVM calls the guard, which is just to check, should I still dispatch to the same method? Basically, has anything changed? And then if the guard says everything is okay, then we'll just call that method again, which then allows the JVM to do all the optimizations, like inlining, all the stuff Rubinius does. That wasn't really possible before with Jvm 1.6. And then if something changed, like if the guard says, no, 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 don't go here, then we'll call the fallback, which is the method that says, please look up that method again and give it to me. And what JRuby does, the bootstrap doesn't do anything, basically. And so the guard always fires for the first request, and then the fallback fetches the method. And you get all the optimizations. And I think by that I'm out of time, and I hope I didn't lose you guys, and hope to have given you a better feel of what's going on in the Ruby implementations. Are there questions?
So you said in Rubinius you are considering doing inline caching.
In
Rubinius you're considering implementing inline cache for the dispatch.
That's already implemented.
Okay.
It's actually just caching one path right now. There's a branch that does polymorphic caching.
Okay.
So basically, with inline caching, you optimize just for the most usual case. But there is one branch by Dirkjan,
okay,
where he's looking into implementing caching more than one path, which is important if you have like one method that is frequently called with two different kinds of objects, which is not that uncommon.
Well, my question is how will you do with concurrency if the same code is executed from two threads at the same time? Because I did inline caching in MacRuby, and we had to revert because we had concurrency issues.
Okay.
I'm not sure if you know.
Yeah, so I am not 100% sure in that case. I know that at some point...
I was wondering if there is a lock inside the cache. Or,
yeah, there is a lock somewhere, but it's working like an optimistic lock, so for the normal execution flow, it's not locking.
Okay.
I'm not 100% sure. I haven't worked on that code, but I can look that up. Or
oh yeah, I would be.
Okay.
Oh, yeah.
Yeah.
Okay. Thank you.
So the question was, what actually happens if like two threads executed in full parallel, which is possible on Rubinius, not on MRI, and then what if two threads try to fill the cache at the same time? My answer was basically I don't really know.
Thanks for the talk. I got one question. It's a bit of mixture between the talk of Laurent before and yours. I would pay big bucks to have a really compiled version of a subset of Ruby that works on Mac and Ubuntu. Have you heard about something like that? I mean, like 10 times faster.
Talk to Terence.
Yeah?
I'm not sure, you're just focusing on Mac right now. But so what you need to do is actually link everything static.
Yeah.
Yeah, and Terence has looked into that with Yehuda.
Oh, you mean Tokaido stuff?
Yeah, just compiling everything, linking everything statically.
In Tokaido? Yeah.
Yeah.
Like with SM and stuff?
Yeah.
Yeah, so looking at linking all the external dependencies that way.
Yeah.
So you have a formal version of Ruby.
Yeah. So if you link everything static, then in theory you could just ship compiled version.
Thanks.
All right, so thank you, Konstantin.